Okay, so I think we can get started. Is the microphone working? Can you hear me? Okay. So from today's lecture until next Tuesday, we're going to talk about hypothesis testing. So before we talk about hypothesis testing,
Just keep going.
yeah, before we start on hypothesis testing, I want to give you an overview of what is the structure that we have covered so far. So we talk about statistical methods, and the first lecture that we had on statistical methods is descriptive analysis. So descriptive analysis is really about describing the sample as is. You're not making any inference that beyond the current sample. And then if you want to go beyond that, that is called inferential statistic. So inferential statistic, the major characteristic of that is really you are using the sample, which is a random sample from the population, to infer population. And when you see inference, it's most likely referring to some parameters of the population. So when you talk about inference or inferential statistic, it typically is in two categories. One is in estimation and the other one is in hypothesis testing. So we covered estimation, and this lecture we're going to start on hypothesis testing. So what is hypothesis testing? Hypothesis testing is really relates to your research that when you have a research hypothesis that conjecture or suppositions that motivate the research. And a statistical hypothesis restate the research hypothesis in a statistical language. So a lot of times when I do consulting or when I do my collaboration, most of the time when I talk with the PI about any statistical question, it always follow this process that the PI or the biologist give me a research hypothesis, and then quite a lot of time is spent on how do you translate a research hypothesis into a statistical hypothesis. And you will see that there are several very important components in terms of this translation, and we will cover that in today's lecture. And formally, what is a statistical hypothesis? What is a statistical language for hypothesis testing? And when you talk about statistically, when you talk about hypothesis testing, you always start with a null hypothesis, and you always have alternative hypothesis. And the null hypothesis is typically represented by H null, H0. And then alternative, sometimes people use H alpha, or sometimes people use H1. But when you see those symbols, it basically stands for null hypothesis and the alternative hypothesis. And what is the process of statistical hypothesis testing? It typically starts from a null hypothesis. And the null hypothesis is set up before you observe the data or before you perform any hypothesis testing. So it's really about your prior belief. And then you start off believing the null hypothesis, and then you collect the data, and then you perform the test. And the major purpose of this test is really trying to see if the data provide enough evidence to abandon our belief in the null hypothesis and towards the direction of the alternative hypothesis. Okay, so it's a little bit counterintuitive, but this is the whole structure of statistical thinking. Essentially, you talk about the null hypothesis before you observe the data. And then after you have the data, all your task is if you want to see if this data gave you sufficient evidence to abandon or to reject the null hypothesis. So that is why most of the time we have the power, or we are able to reject the null hypothesis. Very, very rarely or very informally, you see we accept the null hypothesis, because that is not the right fundamental of statistics. What you do is with the data you want to reject, And sometimes if you turned out to be that you fail to reject, the terminology that we use is we fail to reject. We don't have enough evidence from the data to reject the null hypothesis. So your true outcome is either you reject the null hypothesis or you fail to reject the null hypothesis. When you talk about accepting the null hypothesis, this is typically not the conventional way of putting statistics. Okay, so this cartoon gave you a little bit about more illustration of what I talked about. What is a hypothesis? Hypothesis is really a belief about a population parameter. So this I have emphasized that a lot of times. Hypothesis is really about population parameter because you cannot observe the whole population, because you cannot observe the whole population parameter, and then you need to make a hypothesis, and then you need to perform a hypothesis testing on the population parameter. So there are two characteristics about a statistical hypothesis. The first one is it refers to a population parameter, whether it's mean, proportion, or variance. It could be any parameter. And the second one is the hypothesis typically must be stated before the analysis. So it's set up before the analysis. So let's give an example. So the null hypothesis is, I believe, based on my prior experience, that I believe the mean birth weight in the general population is 120 ounces. So that is your null hypothesis. And then the next step is you take a sample of 100 babies in the hospital that you work, and you measure their birth weight. And you find that the sample mean birth weight from this 100 samples or from this 100 babies is 115. And by the way, this hospital is in a low social income area. So your task is to see whether this low social income area hospital, this hospital have a mean birth weight that is lower than 120, or this difference is merely happening by chance. So essentially, now you have the population that you're interested in is the birth weight of the low social income area, and then the parameters that you're interested in is the mean birth weight of this population. And then your null hypothesis is you believe it is 120. And your alternative is either it's lower or it's different from 120. So this refers to the several important concepts that we talked in this concrete example. So what is a null hypothesis? A null hypothesis is the parameter of interest here is the mean birth weight of this low social income area babies. And let's denote that by mu. So the null hypothesis is essentially that H null means mu equals 120. And that means the mean birth weight of this particular area is equal to the mean birth weight of the general population. And then the null hypothesis doesn't have to be always its equal sign. It can be like less or equal, or higher or equal. But typically, or almost all the time, the null hypothesis contains an equal sign. Remember this. And then a lot of times people make the analogy of doing statistical hypothesis testing with the jury duty, that you believe the suspect is innocent until you prove it guilty. So essentially, you believe the null hypothesis until your sample gives you sufficient evidence to reject the null hypothesis. So this is the how you think that intuitively. And then, what is the alternative hypothesis? In practice, most of the time, the alternative hypothesis actually represent your research goal. So if you want to prove that, or if you want to see that the baby in the low social income area is actually lower than the baby weight in the general population, you actually put that in the alternative hypothesis. So remember, the null hypothesis is something that you wish to, or you are trying to reject. And the alternative hypothesis is what your research is really about. So this is a little bit counterintuitive, but this is how statistical is set up. And then alternative hypothesis should be the opposite side of the null hypothesis. And it doesn't have to be one side or two-sided. Both could work. For example, if you believe that the mean birth weight of this area should be lower than the general population, you can set up a one-sided alternative hypothesis, which is the meal is less than 120. It can also be the other side, which is higher than 120, or it can be just in general, it doesn't equal to 120. So most of the time, conventionally, the alternative hypothesis does not contain the equal sign. The equal sign is always put on the null hypothesis side. That is a distinction. And then if you have a non-equal sign in the alternative hypothesis, that refers to a two-sided test that we often talked about. And then if you have just one direction, less than or higher than, that refers to a one-sided test. So this page gives you a little bit more details about what is one-sided and what is two-sided. So a one-sided really refers to your alternative hypothesis is just referring to one side of the direction. And then the two-sided refers to that both direction, whether it's higher than your null hypothesis value or it's lower than the null hypothesis value, both of those contained in the alternative hypothesis. And a little bit re-emphasize is when you talk about, when you put that in symbols for hypothesis testing, remember that the null and the alternative hypothesis it's always about the population parameter. So here we use mu. So when you see that, if you see my null hypothesis is x bar equals to 0, and my alternative is x bar is not equals to 0, this is essentially wrong because x bar refers to sample. So after we have the setup of null and alternative hypothesis, the essential goal for you to perform hypothesis testing is really to make a decision of whether reject or fail to reject the null. And if you think about it, there are 4 scenarios, and those are the only 4 scenarios for hypothesis testing. The first one is when the truth is a null, when the null hypothesis is correct, you fail to reject the null hypothesis. So that means you're making the right decision. And the second possible scenario is when the true hypothesis is wrong and you fail to reject the null hypothesis. And that is an error. And then the third one is the other side, that if the null hypothesis is true and you reject the null hypothesis. And the last one is when the null hypothesis is false and you reject the null hypothesis, which is also a good one. So given those 4 scenarios, we are putting some names to refer to each one of that. And if you go to this table, that probably is a little bit more clear in terms of those 4 scenarios. So in this table, the column represents the truths, which you don't really know in practice, but this is what is the real situation is. So the truth could be 2 possibilities. Either the null is correct, is true, or the null is not correct, so alternative is correct. And then the two rows refers to your decision. And you could have two decisions. One is you see you fail to reject the null hypothesis. And the second one is you reject the null hypothesis and believe the alternative hypothesis. So given this interaction between the column and the rows, you could have this fourth scenario. The first scenario is if the null is true and you fail to reject this null, so here I actually use accepted, but most of the time you see you fail to reject the null. So that essentially means you are making a correct decision. And if you look at this part, right here, the first column and the second row, if each null is true, and however, your decision is to reject the null hypothesis. So in this situation, you are making a mistake. And what should we call this mistake? In statistics, we call that type 1 error. So we call it an error, which is type 1 error. And conventionally, we use alpha. So what does alpha state? Alpha states the possibility or the probability of making type 1 error. So that refers to alpha. Remember, type 1 error refers to when the null hypothesis is right, is true. However, you reject it. And then if you look at the second column.
So would that be a false positive?
Yes. If you look at the second column, and then this column is essentially based on the alternative hypothesis is correct. So alpha is correct, or H1 is correct. And then if you are in the first row, which means you fail to reject the null hypothesis. So in that situation, it's also a mistake because your decision is not a reflection of the truth. So in this type, we call it a type 2 error. And we use beta to represent the probability or the chance to make a type 2 error. So if you go to the previous context that you're asking about false positive or false negative, this one would be a false negative. And then the last chance, which is when H1 is true, and you are making a decision that you reject the null hypothesis and you believe the alternative hypothesis, this is again a very correct decision because your decision is reflecting the truth. And in this time, the probability of this cell is 1 minus the type 2 error, which is 1 minus beta. And this is typically refers to as power. Yes? Where? Oh, yes. So this is H1 is accepted. Yeah. So what is the relationship between type 1 and type 2 error? First of all, you know that type 1 error only happens if H null is true. Although you don't know the truth, but however, only when the truth is H null, you are possible to make a type 1 error. If the truth is H null, it's unlikely at all for you to make a type 2 error. Okay, and then type 2 error can only occur if the alternative hypothesis is true, which is the null hypothesis is false. And then when you talk about the probability of those two errors, alpha and beta, remember that given a set of decision rule, if your decision rule increase alpha, which means if your decision rules is really it has higher likelihood to make type 1 error, then the same set of rule will have lower likelihood to make type 2 error. So it's always a trade-off that you can't minimize those two given one set of decision rule at the same time. So essentially, if you have one set of decision rule, you're either you are in favor of alpha or you are in favor of beta. You can't minimize the two at the same time. So this is really what I just said before. Okay, so this gives you a process of how do you do hypothesis testing. Again, you start from a population and then you get a random sample. And actually, I mean, although we talk about this a lot of times, like estimation is different from hypothesis testing, but at the end of this lecture, you will see that hypothesis testing actually has a fundamental connection with estimation. So when you do hypothesis testing, it's actually based on, the data is based on your estimation of the sample, of the population estimation parameter, and this is achieved from the sample statistic. So you get a sample and you estimate a sample statistic right here, and based on this one, you make a decision whether you reject or fail to reject the null hypothesis. So essentially that goes back to what I just said, that although hypothesis testing and estimation are different topics, but they are very connected. And why are they connected? Here we are going to, for this lecture, we are going to talk about hypothesis testing on the population mean. So you can see that based on what we discussed last lecture, that the population mean really refers to you know, you are really using the sample mean to estimate the population mean. So here, the basic hypothesis testing of population mean also relies on the properties of the sampling distribution of the sample mean. So here we have the sampling distribution. Hypothesis testing, we assume large number. So we are willing to make that assumption, so central limit theorem can help in here. So this one gives you, if you willing to assume the large sample size, and then central limit theorem helps here, and the sampling distribution of x bar, which is sample mean, is approximately normal. So what does that mean, or how does that help you? It essentially goes to the basic idea of hypothesis testing is you start from the null hypothesis, and based on the null hypothesis, you come up with a sampling distribution of the sample statistic. And then after you have this, you look at what you observed in your actual sample. And then the next step is trying to compute what is the likelihood of observing the sample statistic from your believed distribution under the null. So here it gives you a little bit illustration. Suppose you want to do a inference on population mean. So like I said, you need to go to that. The next step is you need to go to the sampling distribution of sample mean. And for sample mean, we know it's normal distributed with a mu and with a variance. So what do we plug in for this mu here? The fundamental concept here, or the key concept for hypothesis testing, is you always start from the null hypothesis. So the mu here of the sampling distribution of sample mean is what you specified in the null hypothesis, which is 50, suppose. So given this distribution right here, you have 50, which is your null hypothesis value, and then you have the sampling distribution. The next step is you go to your sample and you estimate x bar from your sample. And suppose you estimate 20 right here. So the next step after this is you want to see, suppose the population the population really follows this distribution, really have a mu of 50, that means the sample mean the sampling distribution of x bar should be centered around 50, should be this curve right here. And given that, what is the probability that I observe 20? Because if the possibility or probability that observing 20 under the null is high, that means your data do not have evidence to reject the null. However, if the probability under the null of observing 20 is very low, that means your data doesn't really support that it comes from this distribution. And then you have more and more evidence to reject this mu equals 50. Okay, so this is a fundamental process of the basic idea behind hypothesis testing. You start from a belief, and then from this belief, you have a sampling distribution of your sample statistic. And then you take your data and see where your observed value lies in this distribution, how likely it is to happen. And then you make a decision.
So would that be a type 2 error if you don't have enough data to support 20? Or can you repeat what you just said about whether having a mean of 20 supports but doesn't support the 9?
So here we have not making a decision yet. We're really just describing that, like given the null is 50 and we observe 20. So it's different from the null. But you need to make a decision that how likely, you observe a 20 under when the mean is 50. It's still possible. So the next task for you to ask is really to see whether it's possible, how possible to observe 20 from 50, right? And then based on that likelihood estimate, you make a decision or not. So here we can't really see whether you are making a mistake or not because you don't really know the truth. So essentially, this is what I just talked. If, in fact, the population mean is 50, the next task is how likely that under this mean you observe a 20, or you observe your sample statistic. So if that is the concept, the next tool that you need to have, or the next idea that you need to have, is you need to have a rejection region. Yes?
But you don't know how broad that normal curve is, do you?
No, you do not. You have to estimate from your sample. Yeah. So the next step that, under this framework, you need to, if you think about it, what you're missing is you need to specify what is the rejection region. Because if this is a situation that the mean is 50 and then you observe 20, so basically you need a set of rules that tells you at this region, what is the rejection region that, beyond that rejection region, I will reject. And if it's within, like that, within the opposite side of the rejection region, I will fail to reject. So essentially, in this curve, you need to have a boundary or a region that help you to make the decision. And then you need to compare your observed statistic with that boundary or with that region to make a decision. So this is the rationale of why do we need a rejection region. So rejection region, the definition of that is a range of value of the test statistic x bar for which you are comfortable or you can reject the null hypothesis. So essentially for this range of this region, essentially you need a critical value or a cutoff value to decide, to decide this region. And this one is specified by alpha. And alpha is what we talk about, the type 1 error rate. So typical value of alpha, you can see most of the time is 0.01, 0.05, or 0.10. And this alpha is pre-selected by yourself or by the researchers. And remember, what is alpha? Alpha, like we talked about, refers to when the null hypothesis is correct, what is the probability to reject the null hypothesis? So if you put that in words, alpha equals the probability of rejecting a null hypothesis conditional on the null hypothesis is correct. So for this example, if we think about it more easily from a one-sided test scenario, essentially your null hypothesis is mu equals to 50, and your alternative hypothesis is mu is one-sided, less than 50. Okay, so intuitively, what does that tells you? That tells you if mu equals 50, so my sampling distribution of x bar should be centered around 50. So that means if what you observe is very, very, very smaller, it's quite smaller or quite far from the left-hand side to 50, which is quite smaller than 50, it's more likely to support the alternative hypothesis, right? So essentially, you are thinking like the critical region or the rejection region should be a boundary C here or a cutoff C here, that on the left-hand side of the C, that is called rejection. And if on this side, on the right-hand side of the C cutoff value, you fail to reject. Does that make sense? So rejection region is really just trying to decide that C or that critical cutoff. And how do we decide that? We use this alpha. So this is a trick. Alpha equals probability of x bar of rejecting the null hypothesis when the null hypothesis is true. So if you put that in mathematics, like I just said, you need to have a C. And if your x bar is less than C, it's in the left-hand side of C, you reject. So that means rejecting the null hypothesis in mathematical language, it really means x bar is less than C. So that means alpha equals probability of x bar is smaller than C, conditional on H null is true. So this is how we decide this critical region. Essentially, this green curve gives you the sampling distribution of your sample statistic. It's centered around the null hypothesis value. And this critical value essentially gives you this region on the left side of this critical value, that what does this region satisfy? This region satisfies that the area under the green curve to the left-hand side of the C or critical value, this whole area is alpha. And this area, mathematically, what does it stand for? It stands for the probability of any number is less than C given the null is right here, given the mu is right here. So this is the intuition behind the rejection region. Remember, a rejection region for a one-sided test is you have one critical value, and on the more extreme side of this critical value, it gives you an area that exactly equals to alpha. So if you have a rejection region, then under this green curve, the complement of this region is called non-rejection region. So what does that mean? That essentially means if your observed statistic for, let's say, 20, it's in this region, it's in your rejection region, you reject the hypothesis, you reject the null hypothesis. If your observed statistic is in the non-rejection region, you fail to reject. So this is the usage of rejection region. So, like what I just said, if your observed sample statistic is in this region, you fail to reject. And then if it's in this region, you reject. So intuitively, the C is right here. So if you observe a value that's very, very less than your null hypothesis value, very less than 50, you have a higher likelihood that this value is within the rejection region because it's towards this side of the axis.
How would you modulate this hypothesis testing if you sampled like 50 times or 100 times and every single time you got way below? You know, when it, like if you didn't get below the critical value, but you did it like 1,000 times and you got right next to the critical value, like does that, would you change your mind ever, or is it not contingent at all on the number of times that you sample or the number of samples that you have?
If I understand you correctly, you're saying that you repeat the sample 1,000 times or repeat the hypothesis testing process 1,000 times.
So you set up this way if
Yeah.
you're going to take your sample one time, right?
Yeah.
So if you took your sample 1,000 times and you wanted to evaluate, you know, I've taken these 1,000 samples and I'm right at the edge of my critical value, and it's not, you know, the standard deviation of these samples is very, very small, and every single time I'm getting, for in your example, 21, 21, 22, like 20, 21, right next to the critical value. Would you just continue to say, yeah, but the population mean could still be 50 according to this? Or after you do it one time, is it different than doing it 1,000 times in this instance?
You still confuse me by what is the sampling time that you're referring to. Is that the sample that your sample mean is estimated from 500 samples, or do you repeat that process 500 times? So if that's the case, each time, so here we are talking about hypothesis testing refers to one sample. So it's really like, no, not one sample, it's one time. So it's really about you have 500 samples, and this is the distribution, this is the sampling distribution of the X bar, and X bar is estimated from 500 samples. And then as long as you have this one X bar estimate, you can perform hypothesis testing. It doesn't have to be you repeat the process a lot of times.
Okay.
Do you have another question?
So in this case, you would already, so like you have a population, and do you have any reason for thinking it's 50, or like do you just randomly pick like, oh, I think it's going to be 50, and then it turns out to be 20, or are you saying like you had something to go on, and now you're testing a new thing?
I mean, most of the time you have some prior belief about the population mean. So for example, in that baby example, like prior to your research, you know that the general population has 120. And then so 120 would be used as your null hypothesis value. And this one, like 50, it's really something that you believe, or it's really something that you're expecting to reject. I mean, it could be any value, but then you're conducting a less meaningful hypothesis testing compared to if it's something that quite, like you have some prior knowledge on. For example, if it's 120 and if you reject that, you can make the conclusion that based on your sample, you actually believe, you have evidence to believe that the babies from a low social income status would actually weigh less.
Okay, so the mean is 120. If you took one baby and looked at it, that would be hypothesis testing. But would it be different if you took 1,000 babies? Or is that still just one hypothesis testing?
No, that's a misunderstanding because you cannot do hypothesis testing based on one sample. What I talk about here, the sample size needs to be assumed to be large enough in order for us to use central limit theorem. So X bar is most of the time it's estimated over a large enough sample. So for example, 500 baby or at least 30 babies, something like that. It cannot be like estimated from one baby.
So that's one hypothesis testing.
Yeah, I mean, no matter whether it's 200 or 300 babies and you have an X bar, and then this is one hypothesis testing. You're testing with those 200 babies to answer that question that whether the birth weight in this population is 120 or not.
So when we have different genotypes of like our mice or whatever, and we only have 5 mice per group, and we're doing hypothesis testing, we really can't do that because we don't have large enough numbers, right?
That's correct. When you have that small number of sample size, I mean, doing hypothesis testing, especially today, we are going to talk about one sample test that is essentially based on central limit theorem, and it probably isn't that valid because you only have n equals to 5. We are going to talk about in the last lecture some non-parametric choice of test, and that will help you in that situation.
Okay.
Yes?
So, are you going to talk about the baby experiment in more detail? Take pieces for us?
I don't know, maybe somewhere. Yeah, so what is your question?
Okay, so I'm confused. I think you need to understand. I've never taken a statistics.
Oh, that's fine.
I am completely bewildered at this point. So you start off with your babies, and you have no idea about babies when you start off. So you collect, say, 100 babies, and from this you can get a sample mean,
Yes?
and you can get the variance
Yes.
based on that sample. So then the variance is the thing that would give you the shape of that curve there, right?
Yeah, the width of this bell curve. Yeah.
So you would say, I believe that my variance is correct, which shapes the curve for me. But I happen to believe, again, from others, someone walked into the room and said that the average weight of babies is 120, and I use this separate piece of information, which is not based on any testing that I have done. And then then what I'm doing is I'm testing the experimentally derived shape of the curve and the experimentally derived mean, sample mean, against the externally provided assumption that the mean will be this number.
Mm-hmm. Yes, that is correct.
So in a sense, this is sort of backwards, isn't it?
Backward in what type of meaning?
In the sense that would you not then have take this curve and center it on the mean the sample mean that you obtained, and then test to see whether the externally obtained number satisfied your assumption?
You are correct. I mean, intuitively, like I told you, statistic hypothesis testing is always counterintuitive. You always start from the null hypothesis, and your null hypothesis should be set up before you look at your data. So like 120, someone tells you that. You always start from there, and you get your sampling distribution, and then you think backward. You think basically seeing, if that is true, what is the possibility that I observe the sample mean, which is 115. And then if it's very likely, so you see, that external number someone gave me is correct. I fail to reject it. If it's very less likely, so you see, I reject because it's too small event, too less possible. So this is essentially the rationale behind hypothesis testing is everything is counterintuitive. You start from what you believe in, and then you see would the data have sufficient evidence to reject your prior belief. So essentially, you are seeing the correction. That is the rationale. It's counterintuitive.
But I thought that the mu is the population mean. So you're from the population, you're taking a random sample, and that's your experimental mean. So then mu wouldn't be a random mean.
So here I think your yes and no. The yes part is mu is the population mean of the general baby population. However, here your specific population is a baby in a low social income status. So those are actually two populations. So that is the part that you got confused. And the part that you are correct is the mu is the right choice because the mu of that 120, it actually means something. If you reject this hypothesis, that means that particular baby in those particular population is different from the baby in the general population. That is more meaningful compared to see, I test whether the baby's birth weight is 0, right? So essentially it points you that the good characteristic that when you choose a null hypothesis, be careful and choose something meaningful. But it shouldn't be the population mean that you believe that's specific to your tested population. Okay, so after we talk about the one-sided test, we talk about the rejection region, and we talk about the non-rejection region. The next part is we can extend that very easily to a two-sided test. Remember, a two-sided test is the H-null part is the mu does not equal to a hypothesized value, which is the H-null value. So when you see does not equal, it can be on the right side or it can be on the lower side. So it can be very low, much lower than 50, or it can be much higher than 50. Going to either side or either direction satisfy or more in favor of the alternative hypothesis. So if that is the case, intuitively you should feel that your rejection region should not be on just one direction. It should be evenly distributed across the two directions. So that is exactly what we are doing here. Suppose this is the same sampling distribution of x bar, and under the null hypothesis, it is centered around the mu, which is your under the null, the hypothesized value. And then your rejection region is evenly distributed on the two sides. So either this side or either this side. To make it even, that means each side has an area of alpha over 2. So essentially, if what you observe is either quite bigger than H null or quite smaller than H null, you have higher chance to reject the H null value. So the rejection region is two-parted, and then each area is alpha over 2. And then in the middle, which is the complement of these two region, or which is the complement of the rejection region, is called non-rejection region. It also, if you think about what we talk about interval estimate, this is also your level of confidence, which is 1 minus alpha. So in terms of comparing to what you observed, this is exactly what will happen is if what you observe is either from this side or this side, you reject the null hypothesis. Essentially, the intuition behind that is under this hypothesized value, it is too less likely, it is very unlikely to observe this one. So I have enough evidence to reject the hypothesized value or to reject the null hypothesis. And then if you observe something in this non-rejection region, which means in between these two rejection region, then you basically see that, it's not that rare to observe this value under the H null value. So that means I fail or I do not reject this null hypothesis. Yes?
I wonder if I take samples from two different populations, not just one population, two different populations, and suggest that they have different values. I would use the similar approach or different?
You need to come on Tuesday, because that's a lecture on Tuesday about two population hypothesis testing. So here, remember, today what we have talked about is really one population hypothesis testing. Like you said, one hypothesis is really you are comparing a population parameter to a prior decided value, to a set value. So that is what we are going to talk about today. On Tuesday, we are talking about exactly what you were referring to is, suppose I don't have a value. I just have two set of samples, and I believe they are coming from different population. Or I believe they are coming, or I want to see whether they're coming from the same population. So my task is to perform a test to see whether the population mean of each sample representing is the same or not the same. So that is a situation called two sample or two population hypothesis testing, and that is on Tuesday. Yeah. So again, if you observe on the other side, you also depends on whether or not the observed value is in the rejection region. You fail or reject the null hypothesis. Okay. So after we have talked about those concepts, now you actually have enough tools to perform hypothesis testing. And to do that, this is like a list of steps or process that to guide you through how do you perform a hypothesis testing. And here is what I find from my teaching experience. Like most students would put that aside whenever they do like a homework or something. They follow each step like a recipe. So essentially, what is your recipe of doing a hypothesis testing? The first step is you need to state what is your null hypothesis. And then remember, this is before you observe or perform any analysis. And then you state your alternative hypothesis. For this, you need to think about whether it's one-sided or two-sided. And then you choose alpha. Alpha you can choose between any value, essentially. But most conventionally, people use 0.05, 0.01, or 0.1. And then the fourth task is you get a sample. You can choose an n and to get a sample, or you can just someone gave you a sample and you decide what is your n. And the next part is you choose a test. This is what we are going to teach you for this course, is essentially what scenario use what test. And the next part is based on the test, you need to set up a critical value. And that critical value essentially enables you to specify a rejection region. And then you collect your data and you compute your test statistic, whether it's X bar or it's P hat. And then you make a statistical decision. Depends on your test statistic is in or not in the rejection region. And the last one is to make a conclusion and decide. Okay, so this is the process. And for this lecture, we are going to talk about test for population mean. And here I'm referring to test for one population mean. Essentially, you have one population, and you are testing whether the population mean equals or not equals or higher or lower than a pre-hypothesized value. And most likely, you don't know the sigma as well. You testing for the mu, and sigma, you don't really know that. So this is called one sample t-test that we're going to talk about today. That is because the test statistic follows a t-distribution. So that's called t-test. And what is assumption? What are the assumptions for one sample t-test? The first assumption is if your population, if you believe that it's normally distributed, you are fine. The second assumption is if it's not normal distributed, then you need a large sample size. Here I put 30, but it's not really like any scientific backup behind this number. It's really just a rule of thumb. And then also you believe your population is not heavily skewed. It's kind of symmetric. So under either the first assumption or the second assumption, you can use this one sample t-test. And what is the test statistic for one sample t-test? That is x bar subtract mu over s over square root of n. Why is this one? The intuition, actually, we told you during the estimation 1 lecture. It's because when you test for population mean, remember, it's always based on sample. And what is your estimate, sample estimate for population mean? That is sample mean. And what is the sampling distribution of sample mean when sigma is unknown? I told you already, that's t-distribution with n minus 1 degrees freedom. So essentially, which means that enables you to do a t-test or enable you to use a t-distribution to do a hypothesis testing. Okay, so we put that in an example. So this example essentially is like here. A manufacturer of detergent claims that the mean weight of detergent is 3.25. And then you go ahead and take a sample of 64 containers. And then you calculate the average of your sample is 3.238. And the standard deviation from your sample is 0.117. So the question in the scientific language is the manufacturer correct or not from your sample? Or the manufacturer of this detergent, is it really have the mean of 3.25 as they claimed? So this is a scientific question. So how do we translate a scientific question to a statistical question? Essentially, if you think about it, what is the choice of the null hypothesis value in this situation? The null hypothesis value is the 3.25, which is believed by this manufacturer before taking this example, because they claim that it's 3.25. So that is the null hypothesis value. And then to prepare you for a sample, for hypothesis testing, you also need to select alpha level. So suppose we select 0.01. So if we put in that recipe, what do we have? The null hypothesis is mu, which is the average weight of detergent from that manufacturer, is 3.25. And then suppose we use the two-sided t-test, or we use a two-sided alternative hypothesis. So the alternative hypothesis is mu does not equal to 3.25, and alpha is 0.01. And because you already have the sample, so based on the sample, you can actually calculate the degrees freedom, which is the degrees freedom of the t-distribution is n minus 1. So that's 64 minus 1 is 63. So what is your test statistic? The test statistic is the t-statistic, which is x bar minus mu over s over square root of n. So you plug in those numbers, 3.238 subtract 3.25 over this 0.117 over square root of n, which is 64. So you get this value, negative 8.82. So this is your test statistic. And remember, you are using a t-distribution with n-1 degrees freedom as your sampling distribution of x bar. Okay. So that means, so here it gives you the sampling distribution of t with 63 degrees freedom, which is around 0, and then you have this two critical value from a t table, and this one, each of the area in the shaded area is 0.005, that is alpha over 2. So you got 0.01 over 2, which is 0.005 here, which is right here, and this one is the other side. So the critical value is 2.65. So based on this, how do you make a decision? It essentially means that whether your observed statistic negative 0.882 is in the rejection region or is not in the rejection region. And it seems like it's right here. So it's not in the rejection region. So you fail to reject the null hypothesis. So your decision is do not reject at this alpha level. And your conclusion is there's no evidence that the average is not 3.25. Okay, so I want to give you a little bit mathematics behind this t statistic, and that actually is a review for you, because if you think about it, what we have talked today, what we have talked about the other day is x bar for the sample mean. The sampling distribution of sample mean is a t distribution. And remember what we talked the other day is so x bar, which is the sampling distribution, is t distribution with n-1 degrees freedom. And we actually said that this part is called standardized So the next concept that we want to discuss a little bit is the concept of p-value. So the concept of p-value is actually, at this step, it's actually fairly straightforward because we talk about rejection region. And rejection region, if you recall that is something based on your alpha. You can have this cutoff value which is based on alpha, which is like either it's one-sided or two-sided, and decide that one from your t-distribution curve. What is a p-value? So p-value is, the definition is the probability of obtaining a test statistic as extreme or more extreme than what you actually observed given H null is true. Okay, there are several important components of this definition. The first one is p-value is a probability. Remember that because there are a lot of mystery about p-value. And after you learn this whole course, I hope that at least you can remember or you can interpret p-value correctly. So p-value is always a probability. Okay, so this is the first concept. The second concept is p-value is always estimated under the H null. So p-value always talk about the probability given H null is correct. So this is the second concept about p-value. And the third concept is p-value is a probability. It's a probability under H null of observing the test statistic or even more extreme. So what does that mean? So remember this example. In a two-sided test, a t-statistic that we estimate is negative 0.882. So this negative 0.882 is your observed value. And this curve gives you under the H null, what is the distribution of this t? Okay, so if you just use that definition, what does that tell you? That tells you that if you put 0.882 here, and then you put negative 0.882 here, because this is a two-sided test, the p-value refers to the possibility of observing 0.882 or more extreme. So that refers to this triangle and this triangle. So how do we define more extreme? Under the H null is 0. And this is what you observe. So more extreme means the further far away from the H null, that means it's more extreme, right? So that basically means that it's this region plus this region because it's a two-sided. So essentially, this two region or the area of this two region is your p-value. So the three concepts. First of all, p-value is a probability. It's basically is the area under this curve, so that's a probability. The second of all, p-value is always under the null hypothesis. Under the null, you have a t-distribution with central equation 0. And then third of all, p-value is the probability of observing what you actually observed and even more extreme. So even more extreme on this two-sided test, that means even further away from 0. So the summation of this two area, that is the p-value. So p-value is 0.2 times 2 for this example, which is 0.4. You mean? So here it refers to, so this curve, do you know what this curve is? What this red curve is? And it's a t-distribution with 63 degrees freedom, right? So with that distribution, if you have any value on the x-axis, you can either go to a table or you can go to our R function or a Python function to get this area. Does that make sense? Yeah. So you can get that from a table. Essentially, this area, you can refer to some reference to get that because it's fixed. Because that is because a T distribution with 83 degrees freedom, with 63 degrees freedom is fixed. So if you have any value, you can obtain that area. Okay, so p-value is that area multiplied by 2. And so when you perform a hypothesis testing, you can either do that by the rejection region, or actually after you learn p-value, you can also do that by p-value. So how do you use p-value to perform a statistical test? It basically means if you estimate a p-value, and if this p-value is higher than your priorly specified alpha, you do not reject. If it's lower than alpha, you reject. So this is a set of rejection rule. Yes?
So what's the relationship between P and alpha?
Alpha is you priorly specified. So it's whether it's 0.05 or 0.01. It's a fixed value. And P comes from the table, and then before that it comes from your observed statistic, right? So essentially from this curve, basically you see this is your p-value, and you need to see in like where is the alpha. Alpha, we know that it's always fixed. Once you decide alpha, alpha is fixed. It basically means for two-sided test, alpha over 2 is 0.005, so this value should be 2.6, like what we saw in the previous slide, right, 2.6. So it essentially means that if this purple-headed shaded area, which is your p-value, is bigger than this rejection region, that means your p-value is bigger than alpha. And that means your observed value is within the non-rejection region, right? So you fail to reject. However, if your p-value is somewhere in this alpha region or in this rejection region, which means your p-value is very small, in that case, your p-value is less than alpha. And then it is equivalent to your observed statistic is in the rejection region. And then your conclusion is you reject the null hypothesis. Okay? Okay, so before I go to the next table, I just want to see that there are two ways that we talk today about performing a statistical task or making a decision from a statistical task. The first way is you can find a rejection region based on alpha alone, and then you can compare the C, the cutoff in that rejection region, with what you observed in your test statistic. Okay, so this is the first way. The second way is you can get an observed test statistic, and then you can observe a p-value based on that. And then you can compare the p-value with alpha, and then you can make a decision based on that comparison. The conclusion between those two ways are always the same because they're equivalent. Essentially, they're exchangeable. Does that make sense? Okay, so the last thing that I want to talk a little bit is about power. So what is the power of a test? Remember what we said. Power refers to 1 minus type 2 error rate, which is 1 minus beta. So what is power? Power refers to the probability of rejecting the null hypothesis when the null hypothesis is incorrect or when the alternative hypothesis is correct. So power is a good thing. Because this essentially is, power is essentially the possibility that you lie in, that it's this scenario, which means when the alternative hypothesis is correct, you reject the the null hypothesis. And this is also, if you think about it, in practice, power is probably the one thing that you really want to maximize, because like I said, your research goal is typically reflected in your alternative hypothesis. So most of the time you are hoping that your alternative hypothesis is true. And given that of course, you want to make the hypothesis testing to make the right decision that when the alternative hypothesis is true, I can successfully reject the null hypothesis. So in practice, your most ideal situation is actually this one right here, that when your research goal that framed as an alternative hypothesis is true, and you have enough evidence to reject the null and accept the H alpha. So essentially, you want this part to be as much as possible, or to be to maximize the likelihood of this one. And this part have a particular term which is called power of your test. So essentially, you would like to maximize the power of a statistical test. And given what we have learned today, how do you do that? Or what is the determination? What determines a power of a test? So there are 4 factors that decide the power of the test. The first factor is the true value of the population parameter. When the true value of the population parameter is very, very different from the hypothesized value in your null hypothesis, essentially your null hypothesis is very wrong, or it's quite far away from the truth, from the true value that the sample comes from, then it means that you have a very good power to reject the null hypothesis. And the second thing, the second deciding factor of power is alpha. When alpha increases, power also increases. So that goes back to the trade-off between power and between beta and alpha. When alpha increases, beta decreases. So 1 minus beta is the power, and that increases. So essentially, if you have a higher power, if you have a higher alpha, which means you would like to sacrifice a higher false positive rate, then you become, the test that you're performing becomes somewhat very liberal, right? And then you actually increase the power. The third deciding factor is the standard deviation. So power increase when standard deviation decrease. What does that mean? If you think about that distribution of x bar, essentially, if the standard deviation is smaller, that means the spread of that bell curve is narrower. So in that way, you don't really need to think about what is, you don't need your power to reject the null get increased. And the last one is sample size. And that is the same with the standard deviation, because sample size is the denominator of the S over n, S over square root of n, that is your, essentially that is your standard error. So when you have a sample size bigger, then the standard error becomes smaller, and then you have more power. Okay, so I don't think I have, okay, I probably have enough time. So it's beyond this, like the scope of this lecture, but I still think this would be helpful for you to understand power from this figure. H null. So let me use the other color. So what does that mean? And you have a C which is fixed here. This is your C. So essentially, what is power in this curve? Power means what is the area under H alpha that X bar is less than C. So this whole blue area under the blue curve, that refers to power. So remember, when you talk about power, it's under the H alpha. So it's under this blue curve. And this shaded area is power. And then if you have this figure in mind, it actually helps you to understand what decides a power. The first thing is this H alpha and this H mu is very far away. What does that mean? That means for the same situation, if you have this is your H null under mu 0. And suppose at this time, so this is your mu alpha. Suppose at this time, my mu alpha is right here. So this is my curve. And suppose this is exactly the same C. Remember, C doesn't change. C only depends on mu 0. C doesn't change at all. So if you think about it, now what is the power? Power is right here. It's the area under the blue curve, which is to the left side of C. So you see the power increase from here to here. So that means if the distance between mu alpha and mu 0 gets bigger, your power gets increased. So this is the number 1 deciding factor. The number 2 deciding factor, or the number 3 and 4 is X is sigma and M. So what does that decide? That essentially decides how wide this curve and this curve are. Because remember, the only difference between this blue curve and this green curve is the mean is different. They're under the same variance. So what does that mean? It means if you have the same distance of mu 0 and mu That's the second one. And then when this one gets smaller or this one gets bigger, each of these curves become narrower. So if that's the case, at the same alpha, at the same distance, you still can increase this whole area. So this is the intuition behind those 4 factors.
Sorry, I just want to make sure that I understood correctly. So your C here is the region,
It's a critical value that decides that region.
but it's the whole region under the curve, or is it just that fixed value? So C is equal to alpha?
C is equal to the critical value that corresponding to alpha.
Corresponding to alpha.
Yeah.
So alpha is the area under the curve.
Yeah.
Alpha is the area.
C is a cutoff.
C is
Yeah. And the cutoff is decided by alpha, right?
but alpha is the actual area.
Yeah, alpha is the area. C is a cutoff. Yes?
Will we be learning how to reconstruct what the power of the study was, given we're going to be doing that?
You have enough tool, but will not explicitly tells you that formula. Essentially, if we have more time and if it's a more advanced level class, what we will do is, given that formula, power is the probability of x bar less than c given h alpha, and then you can plug in all those numbers and you can get the exact formula of power. And given that, if you have a sample size, if you have all those different factors, you can calculate a power of any study. But for this course, we'll really just give you the 4 deciding factors that decide a factor. So when you decide a study, when you design a study, and when you want to decide what is the sample size required, you always need to think about in terms of those 4 parameters. Okay, that's it for today. And for next lecture, we are still going to talk about hypothesis testing. But next lecture, we are going to focus on 2 population hypothesis testing.